So let's take a look real quick at one of the most critical components of video as it relates to traffic reconstruction. And that is that video contains variable refresh rates. In other words, the amount of time that passes between any two frames in a file is going to be different than any other two frames in the same file. So when we're looking at the refresh rates of a clip, and it says, for example, that it's 30 frames per second, that doesn't actually mean that every single frame is 1/30th of a second apart. So we can't simply look at the clip and count the number of frames and know then the speed of a vehicle. We have to look a little bit further into the metadata of the file in order to analyze how much time is actually elapsing between those two different frames. So I'm going to show really quickly here a case that we did recently where this was critical, and then let's take a look at another kind of traffic example where this is going to expose those same limitations. This is a case actually out of Canada where a supervisor was tasked with observing video from a booking center and looking exclusively for issues related to excessive use of force that any of the officers might be engaging in while booking individuals into a drunk tank. As he's watching the video, he ends up seeing this event here in a way that I'm going to play forward for you now inside of QuickTime here. QuickTime is not going to be playing back the speeds correctly, but we're going to be able to watch it in the same way that the supervisor watched these events. After observing what we're about to see here, he ended up putting the officer on administrative leave, and they were about to try the officer criminally for about 4 counts of assault for what we're about to see here. And then what we're going to do is look at the way that iNPUT-ACE sees this file and extract out the necessary metadata to look at this with a little bit more of scrutiny. So I'm going to play forward here and speak through the way the supervisor watched this video. So again, these are not my words. This is the way the supervisor watched this. He sees the officer lunge forward, grab the guy, spin him around, and slam his head against the wall. Do you see that? Let's play through that one more time. Lunge forward, spin him around, slam his head against the wall. You see that?
Okay.
All right, so before going too much further, let's take the original file and let's drag that into iNPUT-ACE, and let's take a look at this in a little bit more detail. The very beginning of this file, when we're looking at the very first frames, we can see the timing here listed on the metadata section right here on the file list. And the very first frame is starting at time 0. So 0 hours, 0 minutes, 0 seconds, 0.000. The next frame is 1.001 seconds later. The next frame is 1.001 seconds later. Again, we see that pretty much all the way through the beginning of this file. So it's roughly 1 image per second here at this point in time in the timeline. Later on in the timeline, when that officer is walking with that individual along this hallway corridor here, this frame here is at 6 minutes and 14.309 seconds. And the next frame is at 6 minutes, 14.409. So no longer do we have a 1 frame per second refresh rate. Now we're looking at a 0.1. In other words, it's 10 frames per second now. Every interval is 0.1 seconds or 100 milliseconds apart. You see that?
Okay.
It might look like everything is going forward at roughly 10 frames per second, but here's where it gets really interesting. Once the officer is about to lunge forward, this is the frame right before he lunges forward to move forward towards this guy, and I'm using that lunge forward in kind of in quotes here. The time right before he moves forward is 6 minutes and 17.311 seconds. The next interval is 617.612. So the amount of time that's passed between here and here is 301 milliseconds, whereas the frame before that was only 100 milliseconds. Understanding this is critical when doing things like speed calculations, because if we're counting the amount of time that passes when a vehicle is in a position here versus the vehicle's over here, if all we were to do was to count the number of frames that have passed and assume that those are the consistent amount of timing between them, we can end up getting incorrect results. And so we're really careful to ensure that we're always reporting when that metadata is available, how much time is passing actually between each one of these intervals. In this case, that was critical because the times that he's quote unquote slamming his head against the wall, look how much time has passed between this instance here and this interval here. We've gone from 620.815 to 621.516. That's almost 3/4 of a second that passed between this frame here and this frame here, which is a lot different than assuming that it's still 1/10 of a second and he's quote unquote slamming his head against the wall. We also provide an additional feature here, which is this Save Frame Analysis button. And I'm going to just simply one button push on that button there is going to generate all of this metadata into a single spreadsheet. And we can now go through this spreadsheet line by line and see all of that data in a little bit more detail, and also correlate that with some additional information. So here's the entire spreadsheet. It's basically all of the metadata that's available to us for every single frame, including things like what type of frame it was. So there's that reference of those iframes and pframes again. We can also see the width and the height of the images. We can see what size they are. We can even do some really cool things like seeing what position in the file it is. So actually where that frame exists inside of the file itself physically, which can allow us to do some more advanced things. And what we're looking at right now is the most important field for this particular case is this packet duration time that reports to me the exact refresh rate of every single frame throughout the file. So we can see that 1.001 for the beginning of the file. And then once we get over to these frames here, like right before that lunge occurs, for example, I can actually copy the frame out of this visual right here. And I can find that same clip by just simply searching for that frame number, or that frame position rather. And I can now highlight that exact frame's metadata, and we can see from here, it's that 100 milliseconds, and the next instance is that lunge at 301 milliseconds, and then 1 again, up to 2, up to 301, and we can really report on all the variability throughout this entire clip, including instances where he might jump forward 1.2 seconds. I can also look at the drop-down up here and see every single refresh rate for each of the clips in consecutive order, starting at the smallest refresh, which is 33 milliseconds. So there's at least one instance where there's only a 33 millisecond refresh rate between the frames. And the biggest is 4.2 seconds. So there's one instance where it jumps forward about 4.2 seconds on one of the frames. So can you see yourself using this kind of thing for traffic analysis in terms of calculating the refresh rates between the images?
Oh, absolutely. Like you said, if you're just counting the number of frames and dividing that by 60 seconds, you could in fact be wrong. Yeah,
exactly. And it's really helpful when that metadata is there. And even in some cases when that metadata is not there, like I'll show you another case here. Another level of this is that we've got some proprietary indexing that we're using in the back end to be able to pull out all the data from these types of files. So for example, if I load in this .264 file here, this is another clip that we can play forward that's going to go through and extract out that timestamp information for us down here so we can see that data. I'm actually going to generate another frame analysis on this particular clip, but because this file is about 107,000 frames long, this might take a little bit to start. So I'm going to begin running that, and then I'll talk through this particular case. The interesting part about this case is that we were working on a 3D laser scanning reverse projection case where we're basically calculating the amount of time and distance that passes for a vehicle that's involved in striking an individual that's walking across the street. And the opposing expert on this case, here the report's done now, so I'm going to generate this. Let's call this frame analysis 2. And Excel might take a little bit to open this up again because it's so large. So I'm going to continue kind of talking through this case while that's loading. But he had done basically that exact process where he had simply counted the number of frames. He'd looked at the number of instances, counting kind of forward here and manually going, all right, there are roughly 30 frames in a given second. So assuming that every single frame is exactly 1/30th of a second apart, had calculated the speed. When we came in, one of the critical things on this is that many, in fact, most of the players that can play back this type of file or have gone through a conversion to convert this into like an MP4 file are doing that process incorrectly and actually dropping images. So I'm going to look now here inside of the spreadsheet to find those areas that have been dropped. And then we can look inside of iNPUT-ACE and see the difference between that and the way that something like QuickTime might read the uncompressed version of that file. So again, it's going to take a couple seconds here to load because of how large this spreadsheet's going to be. But ultimately what we're going to do is use the information that we have here within iNPUT-ACE correlated with the spreadsheet to find areas that other players would have been dropping those images. Because again, if we're counting the number of images per second and we're missing images, that's going to dramatically change the speed of any vehicle that's driving by. So here's our spreadsheet now. It's done. And the column that I'm going to look at this time is this column here that's called coded picture number sequence, or coded picture number. And I'm going to do a fancy little thing here of creating a new column. And this new column is simply going to be equal to a current frame minus the frame that came before it. So basically, it's just telling me how many frames later is this frame compared to the frame that came before it. And it should be, in theory, all one, right? Every single frame should be one frame later than the previous frame. That kind of makes sense?
Yes.
The problem is it's actually not all one. So if I filter out all of my ones, I can see all of the points in time where other programs are going to be dropping those frames because of misreading the data. So let's take a look at the one right here where we're seeing 15 frames being dropped on this particular coded picture number. One of the ways that I can really snap to this frame quickly is by looking at the position in the file. So there's that position value again that we were looking at before. And I'm going to use that to kind of snap that frame. So it's the 40,201,968 positions. I know this is kind of an advanced process here, but I think it's important to highlight this to see how people that are using this for traffic reconstruction are using this tool to ensure that they're always looking at the most valid results. So this is the area right here where we're going to be, for example, calculating the speed of this vehicle driving through the intersection. So there's that vehicle. Now what I'm going to do is I'm going to pull up a clip that's been converted into QuickTime here, and let's go find that same exact location. So I'm going to snap forward here to 6/11/21 on the timestamp. So 6/11 here. I'll start at 10, and let's play forward now in QuickTime. So just as a summary, in case it's a bit confusing, what I've done here is I've looked at an area where other programs are going to drop frames. They're going to drop 15 frames here, and I've now found where that position is in the file. So I can now look at the way that other programs see that clip versus how iNPUT-ACE sees that clip. So I'm going to play through this now, and in about 10 seconds here, we're going to watch a car drive through, and let's just observe how that car looks watching it inside of this this version of the clip here in QuickTime. So here comes the vehicle driving through, and then all of a sudden it hangs and skips forward. Do you see that?
Mm-hmm. Yes.
So right there, it's dropped all of those frames until that point right there. Boom. So those frames are simply not readable by any other program other than iNPUT-ACE. And if I look at iNPUT-ACE now, let's play through that same sequence of events, and we see that vehicle drive through, and it's all there for us. And the reason that we can do that is because we understand the ones and zeros inside of the file and can pull out all of the raw frames and ensure that we're reading those raw frames and not getting confused by other metadata in the file that might confuse the program. So for example, I'm kind of jumping ahead here, but this is an example of what iNPUT-ACE is seeing inside the file to read those raw ones and zeros for any given frame. And other programs get hung up by some of the metadata in the ones and zeros and then basically skip frames until they can catch back up. So this is critical for doing things like vehicle speed calculations because we need to ensure that we're counting all of the raw original frames in order to ensure they're getting the correct results.